Okay, so I am going to talk tonight about a topic that is often somewhat tendentious, that people argue a lot about, which is type systems and statically typed languages and dynamically typed languages and how they're different from each other and why and under what circumstances you should prefer to use one or another. And I'm going to try to do this in a relatively low temperature way and not say excessively incendiary things. One of the problems of thinking about this is that in lots of contexts, you might look to science to try and answer questions about what the right thing to do is. And it turns out science does not do a good job at answering the question of what programming language you should use. This is a kind of, it seems like it should be able to, like surely we can like run some studies, right? We know how to do social science. Well, that's a questionable claim on its face. But I think in the context of programming languages in particular, it's especially hard because the kind of experimental subjects you have at your disposal are like, yeah, you're a researcher at university, you can get like a collection of sophomores and have them for 2 weeks or maybe a semester to do something. And like, in principle, nothing interesting can be learned from a collection of sophomores for like a semester. Like there is no pile of sophomores high enough to like amount to anything of interest there, because what you care about when you program is you care about what happens at scale, solving hard problems with lots of people over long periods of time. And so the things you do in the first semester of learning programming just like don't matter at all. It doesn't matter how effective you are then. It's these much bigger things that matter, and you can't do an experiment on that. Like, raise your hand if you would like to be randomized into the group that's going to program in COBOL for the next 6 years to figure out whether that's a good idea, right? It's not going to happen. And so we're fundamentally stuck in a world where we need to talk about things based on intuition, based on personal experience, based on stories. And it's not the best way to make decisions, but it's kind of all we got. So there's going to be a lot of that, and I'm going to tell you my own view and talk to you about where that comes from. And you should take it all with a grain of salt, because this all comes from the particular experience and background I have and the way I like to think about these problems, and you may like to think about them differently. So take it for what it's worth. So what's the problem we're talking about? What's the question? The difference I'm talking about is in some sense demonstrated by the two columns of programming language names. Right? On the left hand, we have typed languages, Fortran, C, C++, Java, sort of more ordinary ones on the top, weird, unpopular ones on the bottom, OCaml, Haskell, Rust. On the right, we have Lisp, Python, JavaScript, etc. Lua is a fun one on the bottom. So I think you probably all have some intuitions and feelings about what these languages are like and what they're good for. I think that people often refer to the languages on the right-hand side, the untyped languages, as scripting languages. Think of them as languages that are friendly, approachable, easy to use, easy for doing small, quick things. What else? Lightweight, right, is I think people often talk about these languages. Also slow, sometimes like crushingly, absurdly, factor of 100 slower, depending on which language you look at. And then the ones on the right, well, these are like at least the ones on there's like the weirdo part on the bottom and the more ordinary part on the top. The one on the top is like the standard professional languages that people use for serious software development. At least kind of historically, one often thinks about it that way. They're the things you use when you care about performance. In fact, the two top languages, on the two columns, Fortran and Lisp, are kind of good representatives of the language. They're old. I don't know if people are aware of how old they are, but Fortran and Lisp were pretty close to the first programming languages. Back in the mid-50s is when they came out. And Lisp was a language used for something that seemed to demand lots of flexibility and freedom. It was originally used by John McCarthy's group for artificial intelligence work. And Fortran was used by physicists for many years and continues to be for high-performance computing, right, for being able to do things fast. And we'll see the performance thing comes up a lot. I think people also find the languages on the left sometimes a little unfriendly. They think of them as harder languages to deal with, languages that are more verbose, more painful to use, and weirdly abstruse for like the last three. Right? So I want to talk about a little bit about the characteristics of these languages, but I also want to try and define some terms, because I think the notion of types is itself somewhat abstract and hard to define, and I think it's easier to understand what types are if you have a few words at your disposal. So the first word is a simple one, values. So values are, in some sense, the data that flows around your language, things like integers or floating point numbers, strings, lists, functions themselves. You can think of as values, at least in many languages. But it's like the data that your program operates on. That's generally what we call a value. The next word is a variable. Right, so what's a variable? A variable, it's easy to confuse a variable and a value, but they're not the same thing. In a program you look at, you see, oh, x equals 3. So in some sense, x is that value, but really x isn't a value. X is a name for a value, a name that points to a value, and indeed, at different points in the execution of your program, might point to different values. You have some function that gets called. It has an argument x. Every time the function gets called, x is something different. Right? So even if the function that you call doesn't itself modify x is changing in the sense that in different invocations of the function, it has different names. So variables will point to multiple different values in different executions of a program. And values are this more simple, concrete thing that you see dynamically in a program as it executes. Whereas variables are things that are, in some sense, more static. They're part not of the running program, they're part of the text of the program. They're kind of lexical parts of your program. Right? And then there are expressions. You can think of expressions as like kind of the thing that's one level up from variables, right? You might have some variable x, and then you can say, x plus y. Well, x plus y is an expression, right? It's a larger construct in your language, a collection of syntax that has some meaning, and both in terms of like what it's computing and how that computation runs, right? So this is our language kind of they're built up out of variables and out of other things in your language. And then into all of this come types. So types, you can think of types in some sense in their simplest form as a categorization system for values. It's a way of grouping related values together into kind of named groups. Like before, in fact, when I was talking about it, I was saying the names of types. I said strings and integers and floating point numbers. Those are all examples of types. And if you want to understand what is the difference between a typed language and an untyped language, is in an untyped language, values have types, right? There's a notion of types even in what we call an untyped or sometimes a dynamically typed language. In a typed language, values, variables, and expressions all have types. Right? So why does this matter? And in some sense, this goes to this question of what does it mean for, why, it goes to the question of why are typed languages sometimes called statically typed languages. It's because this static part of your program, just like the static thing is the code that you wrote, the text of the program that you wrote, has meaning associated with it. When a variable has a type, it means in every execution, no matter what happens in that program, that the value pointed to that by that variable always is of the type indicated. And individual variables have type, but also larger expressions in a typed language also have type. So, x might have type floating point number, and then x plus y, that expression also has type floating point number. Okay, does that broad thing make sense to people? I think we're not supposed to do too many questions, but I want to make sure you're all following along. So, why do we even want types? What are types for? And if you look back in the history, and the history really goes back to the mid-50s, back to the kind of creation of languages like Fortran and Lisp. There were really two purposes, and the first purpose of types was performance. Types are about making programs go faster, in part. So the reason for that becomes clearer if you think about how you would execute a program in an untyped language. If you write some Python code and you add two values together, well, there's a lot of things that might happen, right? If I go into Python and I add, 3 and 4 together, well, that's going to be an integer addition. If I add 3.5 and 6.2 together, that's going to be a floating point addition. If I add two strings together, if I remember correctly in Python, that's concatenation, which is, by the way, super weird and totally a mistake. But anyway, lots of different things happen depending on the types of the values that are added together. And there's an interpretation loop that has some overhead that has to decide what you're going to do. when it sees two values it needs to add together, it has to figure out which of the various possibilities do I need to do. In that interpretation loop, it might cost you a factor of 10, it might cost you a factor of 100, depending on the details of the language. But that's a big difference in the performance of your language. Versus what you get in a typed language. If you add X and Y together and you know they're integers, there's a single machine instruction that you can emit that just does that one addition. So in some sense, the reason that types let you get better performance is they inform the programming language, they inform the compiler and allow it to generate much more efficient code than can be generated in a dynamic language. And it's worth saying there are some dynamic languages to which Herculean amounts of work have been applied to make them perform better, kind of even almost within spitting distance of compiled languages, like JavaScript at its best can be maybe a factor of 3 slower than an ordinary compiled language. But even then, it's way less predictable. It's much, I don't know how much JavaScript programming you've done, but you can make a small change in your program and V8 doesn't like it anymore, and you can have a swing of oh, now it's 1,000 times slower. And that's in part because taking something in a dynamic language and figuring out how to make it fast is a non-trivial affair. You have things like tracing compilers that basically watch the program execute and be oh, those things are probably always going to be integers. And so I'm going to substitute the fast thing, after checking that I'm really in that case and make sure I do the fast thing every time. And those kind of optimizations are fairly brittle. So it's both about performance and about predictable performance, critically. And then the other thing, which I think it wasn't understood quite as early about types, is that types are good for making your program understandable. And here I mean understandable to people, right? Understandable to you as the person working on the program, or understandable to the people that you're working with. So that's kind of the big picture of what they're for. So these sound like nice things. Why doesn't everybody like the languages in the typed column? Why don't we just use those all the time for everything? So they have some downsides, and I want to talk a little bit about what those downsides are and where they come from. So one of the downsides is typed languages are often more verbose. The programs you write in a typed language are often more verbose than the programs you write in a dynamically typed language. And let me make this concrete with an example. So here is a very boring Python function. Truncate with remainder. It takes an input that is intended to be a floating point number. It figures out the integer part of that floating point number, and then returns a pair of the integer part and the remainder, what's left over. Okay, so it's not meant to be a very complicated function. It's short, it's simple, it's pretty clear what it does. Now, let's imagine we had written this same program in Java as it existed in 1995 or so. So this is horrifying, right? It's it's hard to even figure out where the logic of the program is. There's so much garbage on the screen. So what the hell is going on? Well, it turns out Java does not have a built-in notion of a pair, right? You cannot just return a generic pair of things in somewhat different now, but in original Java, there was no way of doing it. So if you wanted to return a pair of things, you created a new class for the result that has two things. And then you sort of explicitly write down what are the two things, and now you have a constructor and getters and kill me now, right? All this extra garbage which gets in the way of writing it in a concise fashion. So Java's better than this now. We don't still have this problem to the same degree. We can now write it like this. So now Java has what are called generics, right? A way of expressing the fact that basically that there are type variables, that you can have a thing that isn't fully specialized. Right? Because in some sense about why didn't you have pairs in Java, it's because every time you declared a type, you had to say exactly what was in it. So you couldn't have a general purpose pair because you couldn't express the idea of a type whose contents, the type of the contents of a thing weren't fixed. But with the addition of generics to the language, you can, and now you can write something significantly more concise than what you did before. So what's the point of this example? The thing I'm trying to get across is that the degree to which the type system makes you do a lot of extra writing has to do in a kind of critical way with how expressive that type language is. Types let you embed some structure that you want to. They let you say some things. They let you describe some aspects of your program and not others. And when they don't let you express the thing in a natural way, you often have to end up expressing it in an unnatural way, and that makes you have to write a lot of stuff. So having a nicely expressive programming language is one way that you can overcome, to some degree, this concision issue. It's worth noting there's other things you can do. So if I look at the OCaml implementation of the same thing, so if we compare the OCaml with the Python, they're kind of unch. They're not that different from each other. And on the other hand, the Java one, even the better Java one, has a bunch of extra cruft. There's extra type declarations all over the place, which in some sense distract a little bit from seeing what's going on. So this is another way that you can get some of the concision back from a typed language, which is you can avoid having to write all these annotations everywhere. And the technique that allows you to do that is what's called type inference. So in a language like OCaml, instead of having to write type annotations explicitly on variables, the types can be inferred by the compiler itself. So if I go over to the OCaml code and ask my editor to tell me what the type of the value is, you'll see on the bottom it says it's a function from float that returns a pair of an integer and a floating point number. And I didn't have to put any annotations there. I was able to infer that from looking at the structure of the code that I wrote. So I don't want to go into too much detail about how type inference works, but these are both having a highly expressive system and having type inference help compensate with this issue of verbosity. It's worth saying it doesn't solve all the problems. I think even so, typed languages in some ways are still inherently, there's some extra verbosity that's hard to avoid, because in some places you do have to be explicit about types, and that's extra information that you have to write that just isn't necessary in a dynamic language. So the trade-off can be made much less extreme, but it's still there. So they cause confusion. That's another bad thing that types can do. Type systems are just another thing to learn, right? If you want to understand a programming language that has a type system, you have to kind of understand the underlying semantics of the value language, like the thing, the machine and how it works and how it transforms data. And then you also have to understand this language that hovers above it, that constrains it, that contains essentially little facts that the compiler knows about how the language is going to execute. You have to understand these two languages, and that's an extra thing to learn, an extra work to do. And also, sometimes these languages are gratuitously confusing. So let me give you a nice example of being gratuitously confusing. So if you think about a nice little Python REPL thing, so if I want to figure out the length of a list, I can write this, and it gives me a nice answer. And if I want to figure out the length of a tuple, it also gives me a reasonable answer. And then if I ask it a stupid question, like what is the length of 3, it politely tells me to go to hell and explains to me why I should go to hell. It says, you tried to get the length of an integer. That was a dumb question. Ask a better question, right? So now, let's do something similar in OCaml. So in OCaml, there isn't a general purpose length function. There's a different length function, more or less for each type. So this is where we get to kind of a verbosity question. So I have to do list.length of my list, or I could do, let's say, string.length of a string. And then if I try and do something dumb, like list.length of the number 3, well, I get a kind of reasonable error. Seems nice. It's a little extra writing I had to do, but it's not the end of the world. So then we want to get the best of both worlds. So let's look at Haskell, which has a significantly fancier type system than OCaml's in various ways. And it has a length function, and I can actually look at it if I know how to use Haskell, which I don't really. Right, so the length function has a type, which I can ask for, which is it takes anything that's foldable. I don't know what that means. And I can take a foldable thing and compute its length. Awesome. Let's look at the length of the list. 1, 2, 3. Oh, sweet, it's foldable. Let's look at the length of the string. Hello. It's foldable. Let's look at the length of the number 3. Ah! A terrible thing has occurred. And this thing could be made much worse if, like, you ask the length of a, I mean, this is just unforgivable, actually. That's just crazy. I don't know how that happened. And then if I do like length 1, 2, 3, like almost there. Yeah, there we go. That's the whole error. So there's some complexity that's added by type systems, and different type systems add different amounts of complexity. There's a bunch of different points you can pick in the design space. You can pick relatively simple, unexpressive type systems. You can pick super expressive type system with lots of fancy features. But the more you go in that direction, sometimes you get like truly like terrifying PhD requiring error messages to understand. And even understanding some of what's going on in the type system can be hard, even separate from the error messages. So you want to look for some kind of sweet spot, a place where the type system is expressive enough to let you do things concisely and still kind of possible to understand, and the error messages aren't too confusing. And that's a hard design problem. So sometimes you have programming languages that do that really well, and sometimes they do it less well. And so this confusion thing is a real problem, right? I think there's lots of language with the type system. Some of them are well designed, some of them less well designed, and you will experience some pain along the way. Type systems can slow you down, right? I think that all in, I have lots of good things to say about how type systems help you be a more effective software engineer. But if you're just doing like a little small thing, it's often the case, somewhat depending on the language, but it's often the case that having to think about things at the type level will make it take a little longer to do. Like, it's often easier to write a little chunk of Python than it is to write an OCaml program for doing the same thing, especially at small scale. And it slows you down in the sense that, as I said before, there's new things to learn to really be an effective programmer in a typed language. And then the other kind of subtle thing is that type systems can interfere with your plan. They can get in the way of the thing that you want to do. In that type systems are good at expressing some things and bad at expressing others. And if there's something you want to do in your program that doesn't quite fit the plan that the type system has in mind, it can be extraordinarily painful. And that is, I think, again, a problem that differs between different typed languages. If you look at a language with a very expressive type system like OCaml or Haskell, you have less of that. If you look at a programming language like Java, you end up with more of that. But it's an important trade-off when you're thinking about what you want to do. There are some cases where it really, there are people who are, they know all the things that can be known about how typed languages are put together, and prefer to use untyped language for some kinds of work, because for some kinds of things it frees up the design space. So I think that's a real issue with the problems of types. So how do types help? After all, I really like type systems, so I think they help for things. So we already talked about improving performance. I think that's a very important aspect. They're also really good for detecting errors, finding mistakes in your code. And I think people often underestimate how useful programming languages are finding for errors, because they judge type systems by the bad ones, right? Like, Java's okay at finding errors, and there's some class of things it will find for you, but there's a wide variety of type errors that are not effectively found by a type system like Java's. One example which comes up a lot is null pointer errors. Right? Null pointer errors basically don't happen in OCaml or Haskell or Scala, like literally just don't happen. Right? And there's a whole class of bugs. Tony Hoare, who invented null pointers, famously referred to it as his $1 billion mistake, because of all the cost of inventing null pointers have had on the software world. I think he probably underestimated it. And it turns out that programming languages with really rich and expressive type system can catch all sorts of errors that you don't necessarily imagine they can. Let me give another little example, although running short on time, so I'll probably start doing fewer examples. So here's a trivial piece of Python code. Here's what it's supposed to do. You give it 2 dictionaries. For every key that is in both dictionaries, you want to check whether or not they have the same data. And if they have the same data, you want to add that to a list of elements that you're building up. And those are like the list of places where you have found mismatches between the dictionaries. Okay, so that's what this code is supposed to do. But it doesn't. It does the wrong thing. If you run this piece, so if you look at the dictionaries down here that I have in the example, among the keys that are shared between the two, only the key A shows up in both with different values. But actually, this is going to print out also C. It's going to report A and C. So it just gives you the wrong answer. Why does it give you the wrong answer? It gives you the wrong answer because d2.get of key returns none. Right? And I didn't notice, that it returned none, and I just compare it for equality, and it turns out it's not equal to the thing on the other side. And so it just kind of silently gives you the wrong answer. So this is not the kind of error that people traditionally think of as being a type error. Right? Why? Because type errors are like, oh, I was supposed to put in an integer, but I really put in a floating point. But here, this is just a logic error in your program, right? You just wrote the wrong thing. So how is this a type error? Well, let's look at what the same code looks like in OCaml. So you're all like deeply unfamiliar with OCaml, I imagine. So I don't expect you to understand the syntax, but this is not idiomatic OCaml. This is not, I'm writing this with like using the same kind of side effecty idiom that you would use in Python. But that's not really the interesting part. So the interesting part, so I wrote the code the same way, and it has the same bug, but it has something that it didn't have in the Python version, which is it has a type error. So that little red line says, oh, there's something wrong. And if I look at it, it says, this expression has type A option, and A here is a type error. I mean, it's some kind of option. I don't know what has to be on the inside, but it has to be an option. And an expression was expected of type int. An option is a type that's used to explicitly reflect the fact that something might not be there. In a language like Python or even Java, everything might not be there. Everything is potentially nullable. Everything might be absent. In OCaml, things have to be marked explicitly in their types. And the mistake we made before is now a compilation error, right? I will catch this as soon as I try and write the code. And I can just fix this by doing a pattern match. And here, what I do is this is a kind of data-driven case analysis. I say, oh, if it's none, well, I'm not going to do anything. And if it's some of some data I found, well, then I will do this. Ooh, and now the type error happily goes away, and the code is correct. Right? So I don't mean to overstate the magicalness of this particular example. I think, in fact, it's almost impossible to convey the efficacy of these kinds of disciplines in a small example because they don't really play out in the small. You really see the benefits of these when you look at large-scale programs. But the main purpose of the example is to highlight that the kind of mistakes you can find aren't just the simple, oh, this type didn't match that type. It's not just like you put the tubes together and like they didn't match up. You can find real semantic bugs when you do a good job of designing your program to really use types effectively. All right, so now I'm definitely over time. So let me say a few quick things and I will cut to the end and we can do questions from you all. So another very important thing that types give you is they communicate information. So the type signature that's written down on something, it's a form of documentation. It tells you something about the structure of the function or object or whatever that you're using. And it has one advantage over all other forms of documentation, which is it's true. Right? Documentation is often full of lies. People make mistakes, both when they write the documentation in the first place and even more when they modify the code over time. Types at least get it right. And the more informative your types are, the more you can encode in this guaranteed true way. So there's a lot of value with that. Another very powerful thing that types do is they give you a lot of kind of built-in refactoring power. The kind of invariance that type systems give you tie together parts of your program in a way that you can make modifications to one part and the type system will guide you through the process of changing the rest of it in a way that is sometimes shockingly effective. We have lots of interns who come through our program who they learn this programming language and think it's kind of nice and whatever and not really all that exciting. And then you get to the part of it where they wrote their project and someone code reviewed it and told them the 63 million things they had to modify and they went and refactored their code and they're like, wait, but at the end it still worked. That was weird, right? And this is not the experience you have as programmers, right? You guys are at various levels of programming now, but you all share something, I would like to think, which is you're all terrible at it. Because you're human and people are bad at writing programs. And this whole experience of like being able to do a lot of complicated work in a program and just have it work, if you haven't experienced before, is kind of shocking. And I think type systems can give you that. Again, not all type systems. Different type systems are differently effective at it. Do not judge this by your experience programming in C, because like it's got a type system, but it doesn't help you in quite the same way. But depending on the language, you can get lots of benefit, and different languages are good at helping you in different ways. But you shouldn't guide it by the lowest common denominator. It helps you enforce invariance. A lot of building programs is figuring out what's supposed to be true about them and making sure those things remain true as your program evolves. Types turn out to be good ways of doing that. So there's lots of fun examples there, but I don't think I have time to go into them. But it's often useful to think about invariance when you program, and types help automate some of that thinking. And anything you can get to be done by a computer instead of you is great. Like, programmers should be lazy, including trying to avoid thinking about the hard things they don't want to think about. And then finally, tools, right? Tooling support is often made much better in the context of types. And that's because types aren't just good at explaining your program to you, they're also good at explaining your program to tools that you use. And those tools can then explain all sorts of things to you. And you see a lot of push towards type systems in this sort of JavaScript world, driven to a large degree by tools. Okay, so very quick final thoughts. So don't judge types by their worst face. Right, that's, I think, an important thing to remember. People often come to this sort of divide between programming languages and types and untyped languages by comparing Python and Java. And like, those are not the only 2 points on the spectrum, right? There's lots of other languages you can look at, and there are places that have better trade-offs. And so before you judge, you should understand a little bit more about, the possibilities. Don't forget that there are trade-offs. Like, I've talked a lot about how I like types and how useful they are, but there are cases where untyped languages are easier and nicer. But just like really think about it and understand what the trade-offs are, what are the problems you're doing. You know, if you care mostly about performance of the system and its correctness critical, and you're doing it on a large human scale with lots of people interacting on the code base, I recommend you think about using type systems. If you're doing stuff where it's like really important to get something simple out quick, and you want easy accessibility to lots of people to the system, maybe untyped languages make more sense. But you should really think hard about the trade-offs when you're picking. And finally, I encourage you to learn about them. I think type systems are an interesting aspect of programming language design. I think there's a surprising richness of different approaches to building type systems. And you will be a kind of better and more effective consumer of programming languages if you have experience using a number of different ones that approach this problem in different ways. Okay, and I guess now we get to the part where it's like socially acceptable to leave. Thank you guys for.
We have 2 requests. One is to make sure that your question is actually a question and not a statement in disguise. If you would like to tell Ron anything, I think he's fine with that.
Sure.
After the Q&A. But please keep the Q&A to questions. And the second thing is, if you have a question that you're not really sure about asking because you don't feel like it's a great question, please ask it anyway, because it's very likely that somebody else in this room has the same question. That's it.
All right.
You started by saying that we can't really study this scientifically and gave 2 points that weren't really good, like high-level sophomores and 6 years of COBOL. Do you think there are any other points that are better trade-offs there in a way that we could study this more scientifically?
So I think there are definitely things that people have done that are somewhat better than those 2 terrible extremes. But I'm not, I guess, to say the obvious, I am not a social scientist, and I don't have lots of training in the area. My only real experience is having looked at a bunch of these results, and based on the methodology of things I've seen, I've tried to studiously not get excited about the results that happen to support my side of the argument, because my overall sense is the actual research that's out there, while a lot of it is like good research that's well-meaning, is not terribly convincing. A thing that people have done is to try and mine open source repositories for information about error rates. And I do think there are probably good bits of information that you can extract from that, but the data is enormously kind of biased, full of all sorts of influences based on, like, the language choice does not attach uniformly and at random to application and to programmers. There's an enormous number of bias in what actually gets on GitHub in different languages. And so I think it's very hard to figure out how you would correct for those kind of biases. So I still think, there are interesting kind of conjectures to try and get from that. And those data sets seem to me the best kind of source for this kind of analysis I've seen, because they at least reflect real work. Whereas people get super confused by just looking at students. So I've seen some interesting research on how to do a better job of generating error messages for ML-like languages and also for Java, that's based on looking at the kind of horribly broken code examples that people in their early programming classes enter in. And that has so if you tune for that, it gives you one set of suggestions for kind of how you want to optimize. And in fact, a lot of the approaches are these kind of Bayesian error minimization kind of things of let's find the smallest, simplest, highest probability explanation for what you got wrong. And that's great for some kinds of things and terrible for others, because if an experienced programmer will often modify one piece of their program and see the type errors sprout up everywhere else and be like, oh, okay, these are the things I need to fix to make it match with the change I made up here. But the algorithm that was suggested by the researchers has the property says, oh, you probably wanted to undo that change you made. It's like, no, I didn't. Actually, that's exactly the change I wanted to make, and you have made the wrong inference. And these kind of mistakes are not as obvious when you just look at the terrible code written by a bunch of people who've learned to program for just 2 months. So it's hard. I think there's some good things, but I don't know of anything great.
You mentioned that among languages that do have types, some of them are more useful than others.
Mm-hmm.
So I'm curious what the tangible characteristics are that differentiate the better type systems from the worst ones.
So, beware of my biases in this matter. I have my own languages that I particularly like. I think there's a few language features that I think are outsized useful and surprisingly not as prevalent as they should be. One of them is type inference, which is, it's not the biggest deal, but it just gets rid of a lot of grit in the wheels, and makes it easier to use these languages that have lots of other benefits and kind of just reduce the constant overhead. And that's getting more common. C++ now has type inference. C# has type inference. More languages are getting it, so that's one thing that's becoming more common. Another, I think, very clear example is algebraic data types, which is basically, it's a simple thing on some level. Every programming language on Earth gives you the ability to do what's called a product type, which is to say, I want to put a bunch of things together in a type, like an object or a struct or a record. It's it's got this field and that field and the other field, this and that and that. That's a product type. Everyone supports it well. A sum type, also something called an algebraic data type, a sum type is where you have kind of the dual to that. I want this or that or the other. I want to express a disjunction, multiple different possibilities. And giving you a clean way of expressing that and a clean way of exhaustively reasoning about those in a way that makes sure that your case analysis is complete is incredibly useful and surprisingly rare. The most popular languages that have support for this are, I'd say, Swift and Scala. And beyond that, there are kind of and that's relatively recent. Swift's certainly very recent. And other than that, there's almost no mainstream languages that use that, which to me is kind of mysterious. I think actually a general interesting fact about programming language evolution is it's in some sense shockingly slow. Good ideas, obviously clearly good ideas, can take an amazing amount of time to land. My favorite example is garbage collection, invented in 1957. Mainstream, I'd say with Java in 95. It's a nearly 40-year gap between invention and mainstream use. So there are some technical reasons about, Java garbage collection was initially too slow for this or that, whatever, but there's really no excuse that can explain the nearly 40-year gap there. And I think with things like sum types / algebraic data types, I think there's a similar story where my view is they're really useful and it's just a mistake that they are not more commonly available. There are some other features that I think are nice that hang together well with those, but those are among the most important, I think.
How are some of the ways that you use OCaml's type system? How have those changed over the last decade plus?
It's changed a surprisingly large amount. Oh, sorry. The question is, how are the ways in which we've used OCaml's type system changed over the last 15 years or whatever of using OCaml? It's changed in a bunch of ways. So first of all, the language itself has evolved. There's been a bunch of new features to the type system that have turned out to be useful. I think turned out to be useful because in my estimation and the estimation of other people at Jane Street, I think we did not know that these features would be important. One feature that's turned out to be highly valuable is a thing called first-class modules. So one of the nice things about OCaml is it has a very powerful module system, which is, you think of modules or like programming units, just a way of like grouping code and giving it interfaces. But in OCaml and more broadly in the ML family of languages, you have a powerful system for like constructing and manipulating and building new modules out of old modules. So that's like a great thing that's been there like since the mid-70s when these languages were invented. But making those things first class, so you can take a module and like pass it around to a function and store it in a data structure and all of that, is a new feature which has turned out to be important and given us sort of better and cleaner ways of expressing highly modular programs. Another language feature which turned out to be very useful is a thing called GADTs, Generalized Algebraic Data Types. If you did not feel sufficiently confused with algebraic data types alone, there are generalized algebraic data types, which have turned out to be useful in ways that we really didn't anticipate. It's a thing that seems like it would be really good for modeling something like the abstract syntax tree of a programming language. So it sounds like and sounded to me like exactly the kind of garbage you get when you allow compiler writers to design your language, and they like add stuff to the language that's good for writing compilers, but I'm a systems programmer, and I don't want to write a lot of compilers, so why do I care about this? And it turns out GADTs, we've discovered, are really good for systems programming, and particularly good for writing very high performance code that gives you good control over the structure of memory and layout of memory, while still giving you a pleasant programming interface. So those are like some language features that we've used more and more of. I'd say in general, we've just gotten better at doing typeful design, better at encoding more invariance and structure into the type system in a way that makes libraries easier to understand, easier to use, and harder to misuse. I think people often sort of have a kind of slightly negative, like, this is all about like constraining people and restricting, and type systems are about, stopping people from doing things, and that's not nice and stuff. And I think you can think about it that way, but you can also think about it, it's a way of encoding structure in your libraries, which is kind of easily shareable by all of the people who are using it. And it gives you the ability to, in some sense, construct things which prove facts about your everywhere where this library is used, rules about how it's used, and that lets you reason more about your program and your library and how it can be used and how it affects the overall structure of what you're doing. And that's a thing that we've kind of pushed more and more at doing, and I think it adds a lot of value in that it makes it easier to build software that fails less often and is easier for people to use and easier to upgrade and make changes to, easier to refactor and have those refactorings naturally flow through the code.
What are some of the pain points you went through adopting OCaml?
So in some sense, early on, everything was easy because maybe everything is just easy at small scale. Right? When you're just, a few people, you can almost not know what you're doing. And I was the one who brought OCaml into the organization like 15 or so years ago, and I totally didn't know what I was doing. And anywhere, I think maybe now all of the code I wrote back then has been like ripped up and burned as it should be. But anywhere any of it remains, it's all terrible. But even though I didn't know what I was doing, in some sense it was relatively easy because it was still like a nice, performant, easy to understand language. And at fairly small scale, it was kind of easy to build systems with it. I think as time has gone on, we've seen more pain from the fact that, like in any language that's not very popular, the tooling isn't so hot. And so you, in the end, have to do a lot of investment to make the tooling better. And we've done a lot of that. One of the things I've been involved in is we have a tools and compilers group that focuses on improving the OCaml compiler and building tools. And any organization of our size really should have some kind of tooling group, but we've had to spend more time and put more effort into that. everything from documentation generation to IDE-like features like type throwback and go to definition and auto-completion. And we've actually ourselves put lots of work into that, lots of work into the compiler itself, work into the optimizer. And so the need to do that, I think it's less about any particular thing about the language, which, say, the language itself, there aren't really a lot of pain points on. I think it's mostly just like a pretty good and easy to use language, but there's lots of pain associated with the kind of minority nature of the language, the fact that it's just not very popular.
So given that like algebraic data types are becoming somewhat mainstream now, what do you see as the thing that is like currently obviously good and should exist but does not exist in languages?
So one thing that I wish was available in more places was a mainstream language that is not the result of a car crash. Almost every language that has taken, maybe every language that has tried to take these kind of features to the mainstream has done so in a way that is made worse by the fact that it has done to some degree a good thing of like engaging deeply with the legacy ecosystem. If you look at Scala or F# or Swift, each one is the result of a nearly deadly car crash between two different programming paradigms. Right? In Swift, it's the car crash of Objective-C and essentially ML. In Scala, it's the sort of Java ML car crash. F# is also the kind of the .NET ML car crash. And those car crashes add a lot of extra complexity. And sometimes people add like yet more complexity. Like Scala also has had like a lot of papers like, crowbarred in there. Maybe more than like strictly speaking needed. But I think in some sense, the thing that I like most about OCaml in particular is it's actually a fairly simple language, right? If you're unfamiliar to it, it seems complicated, but it's actually a lot simpler than many other mainstream languages because in some sense it just kind of opted out of this whole thing. It's like, no, I'm just going to like be a relatively good Unix citizen and have good C bindings, and beyond that, not do anything to integrate with other toolkits. And there's a cost to that, right? Because there's a lot of benefit of being inside the JVM, say. But the kind of clarity and simplicity of design is hard to recover once you've kind of made that bargain.
You talked about how generalized abstract data types.
Generalized algebraic data types.
Generalized algebraic.
Abstract data types are another thing, also good.
Generalized algebraic data types were useful in systems programming because they give you like the nice combination of control over what memory is structured while also being expressive. Is that right?
Correct.
Yeah. Could you give an example of how that happened?
I'll try and do it relatively quickly. If you're going to write a program that needs to consume and emit UDP packets, say, and be able to handle a few million messages a second, you have very few options. Here's how your program will work. You will have a region of memory into which you DMA stuff from the card. You will read some bits off of that memory, and you will mutate some data structures on the side, and then you will do it again. That's it. There's no other conversation. You will not allocate anything. You will not construct a future to represent blah, blah, blah. That is the physical structure of how your program is going to run. So the question is, how do you make that livable? How do you make that like a nice programming environment? And it turns out GADTs give you a nice way, without doing any allocation at all, of essentially being able to kind of refine. You get like a message and it has like a big type variable. It's like, oh, I don't know what kind of message it is. It could be a TCP packet or a UDP packet or I don't know. And then you can use GADTs as a way of kind of refining that type variable and say, oh, it's a TCP packet. Oh, and then you can further refine it by using GADTs more. Say, oh, now I know it's a TCP packet containing a NASDAQ message. And now I know inside of that NASDAQ message, it's an add order message. And basically GADTs give you a natural way of making what in the end is a simple flat region of bytes and making it feel like the ordinary combination of sum and product types that you get in a language like ML. In ML, you often structure things as layered combinations of ors and ands. It's this or that, and inside of this, it's this and that, and inside of that, it's this or that. This kind of layered and or structure is surprisingly powerful, but it's normally tied to a very specific memory representation, which requires you to allocate things on the heap. And GADTs let you get something that's logically the same as that structure without doing any allocation. So that's probably like abstract enough that it's confusing enough for a large enough fraction of the audience. I'm happy to go into more detail on that offline, but that's at least like the flavor of why it's helpful.
Are you like encoding if statements into your type system?
Let's talk about it later. It's a little complicated.
What do you think about when a type system is added as a sort of layer on top of an untyped dynamic language, and specifically like JavaScript, TypeScript, and Flow?
Right. So I have not used those languages. Python is also starting to do this. PHP is another language which this is being done with. There's this hack language out of Facebook, which is a gradually typed PHP variant. By the way, the amount of lipstick that has been put on that pig is astonishing. Like PHP, but this is a completely unrelated rant, but I can't resist. If you look at the standard library of PHP, a number of the original functions are kind of weirdly named. Like, why are they weirdly named? These are kind of unusual names. Why is that? Well, it turns out early on in the design of the language, the hash function that was used for looking up functions from their name used strlen as the hash, which is to say it looked at the length of the identifier for identifying the hash buckets, which meant if you had too many functions of the same length, it would be inefficient to look them up. And like this, by the way, to power forward with this, you have to understand the technical problem and decide that the right solution is not to fix your hash function, but instead to twist your standard library into a knot. And this is not totally off topic, because in the end, if you take this thing and layer a type system on it, and like, talk about car crashes, right? That's my concern with these kind of languages. I think in the end, you're taking two very different disciplines and trying to marry them together, and it is at least tricky to do well. Some of the results seem good. Some of the results seem complicated. So one of the really nice attempts at this is a thing called typed racket. So racket is a Lisp/Scheme-like programming language, which is designed for teaching. I highly recommend Racket if like you're teaching your 11-year-old how to program. I think it's awesome. It comes with a variant called typed racket, which has a type system on it. And the problem with typed racket, although it's in many ways a very kind of effective technical feat, is that it tries to really match how Racket programmers actually program. And here's an aspect of how Racket programmers program. There's this thing called the numeric tower. When you add two numbers together, and it's too big to fit in like an ordinary integer, it just becomes a big num. If you take the ratio of two numbers, it becomes a rational. If you take the square root of a negative number, you get an imaginary number. Like, it has all these different possible kinds of numerical representations unified in one very natural mathematical form. But the performance of that is no good, right? If you want to like get the single instruction that adds two ints together, you have to actually know that you're adding integers. So there's this incredibly refined type system, which has a different type for integer and floating point number and rational and positive integer and non-negative integer and 0 and 1 are all types. And there's a lot of engineering in the system to make sure the system never has to actually show you the type of plus or anything like it. Because plus, well, you have to know that 0 plus 0 is 0, and 0 plus 1 is 1, and positive plus, and like non-negative plus 0 is non-negative, and so on and so forth. And like, it's an incredible, like almost every like basic theorem about how integers like line up in terms of like how they transform between different sets gets embedded into these basic operations. So that's one somewhat extreme example, but in general, trying to match the real world techniques used in a dynamic language, which aren't always easily typable, is a problem, right? Typed languages are compromises. They are conservative approximations. They don't get everything right. So the things that people do in a dynamic language often don't quite fit. And so making languages that do both well is hard. So typed racket is one I've looked at in detail and know a little bit more about. I've actually like used it. Hack and Flow and TypeScript and Dart and so on and so forth, I don't understand as well. One interesting part of that world is that some of the languages, some of the type systems that people come up with, they said, you know what? We don't need to get this right. We're going to have an unsound type system. And an unsound type system is one that's like is sometimes wrong. It says things are good when they're not. It doesn't. And This has been made in part consciously because the correct thing is kind of hard to understand. So they've chosen the incorrect thing so that it's not confusing to people and you can still get some of the kind of better tooling that you get by having some kind of type system. That's also a very complicated design choice. I think there's some regret in that community because making that design choice makes it hard to do things like better compilation, because if you can't trust that the type system is actually right, you can't rely on it for compilation, or it's going to take a correct program and make it incorrect. So anyway, I think it's a big, complicated, very interesting research area. And I don't know all the details, but I think there's interesting work there. But I definitely don't want to program in those. If I have a choice, I want to program in a language that was designed for a type system from the beginning. Yeah.
You said that type languages slow you down, or that's one of the things that can happen. And before Jane Street, you went to OCaml, functional type language. What was it like to explain to the team or the company that, hey, we're going to go to this thing, and so we can't move fast and break things, but we're going to move slow and get things right, maybe?
So first of all, I should say, I think typed languages slow you down in the small and speed you up in the large. So I didn't think at the time, and didn't make the argument to people that like it was going to slow us down, but we should do it anyway. There are other things we've done that have slowed us down. We're very careful. We're especially very careful about the things that like send orders to exchanges, because those are scary, right? Like you have a program that you're writing that has access to the markets in your wallet at the same time. You should be a little afraid of that. And so we do a lot of quality control and code review and various other things that is a very clear trade-off between, you know, moving fast and breaking things and getting it right. And we lean much more in the getting it right direction. But I don't think using typed languages was a trade-off of that kind for the kind of scale of things we're doing. A good example, by the way, where a dynamically typed language that we are kind of show clearly is better, we have a contest that we run sometimes on campus, sometimes with our interns, which is an electronic trading competition where we have a little fake exchange, you can connect to it and do stuff. And people often try to use OCaml for it. And it's like, it's a mistake. You're probably better off using Python. If you're like spending like, 12 hours in a row hacking something together as quickly as you can, like maybe if you're like a really good OCaml programmer, but you're probably not, and you should probably just use Python. So like that's an example where of the kind of scale where I think the dynamic language clearly wins. In any case, in our world, we weren't thinking about a dynamic language versus a static language. We actually, our initial trading systems were, and you're surprised we're still in business, VBA in the back of a spreadsheet, which is untyped. But we were moving from that to other languages like Java. And so really between Java and OCaml, that was kind of the choice that I was involved in. And there I think OCaml was just kind of strictly faster and easier to use than Java was. So I think that was not as hard of an argument to make.
Interested in the relationship between types and testing. So a lot of times with dynamically typed languages, we'll just throw a lot of tests at it and that'll catch some of the bugs that might slip in, or as we're making refactoring, that kind of thing. So do types, how do they affect the approach to testing?
Right, so to say what perhaps should be obvious, you need both. You need test and types. Certainly, you can, if you're in an untyped language, obviously you can live without types, but if you have access to both, you should use them both. I think one dynamic you have is that types allow you to greatly reduce the number of tests that you write, because many things that you might test manually are automatically caught for you by the type system. And so you can just spend your testing time more wisely. And I think especially for simple things, you can get surprisingly far by like not doing very much testing at all. Like when I started and didn't know anything, I relied heavily on the type system and didn't do very much testing because I didn't really know what I was doing, and the things I was doing were relatively simple at the time. And it's kind of shockingly effective. When you first start programming in ML, in particular, OCaml or one of the other variants, there's this weird thing that it feels like all the bugs go away. And this is, of course, a lie. Not all the bugs go away. But a surprisingly wide variety of routine bugs that you would otherwise spend a lot of your time on just kind of vanish in a puff of smoke. But testing is super important, and I think one of the ways in which our approach to programming has changed is we have spent a lot more time over the years investing in having good infrastructure for testing, which I think is critical. I think people don't mind testing if the tools for it are really good, but if they're not, they hate it. It doesn't feel like real work to write tests, and it's work and it's important, so you want to make it as pleasant as possible. And so we put a lot of energy into that. And I think the two, in some sense, complement each other. Another thing that's interesting about well-typed programs is they're not just right? It's not like you fix all the bugs, but in a lot of domains, well-typed programs have this kind of snap into place property, which is if you've written it reasonably well and it type checks, then often just testing an example or two nails kind of all the behavior into place. You catch the wide majority of bugs for relatively simple things. So in some ways, type systems amplify the power of tests by adding kind of more rigidity into the behavior of the program that you're dealing with. Okay. Someone new?
So one thing that you mentioned, but I think you really have time to go into, was how type systems help you define a lot of invariants in your program.
Mm-hmm.
Can you talk more about what sorts of invariants, besides the obvious, like this is an integer, you can find and how that's helpful?
So probably the most important class of these invariants are what I might call data dependencies. So you'll often find yourself in many languages building an object with a bunch of different fields, and then one of the fields tells you something about like the kind of thing this is. And so depending on what that field is, what's in other fields is going to be different. So there's a dependency between different fields of the object, and then there are some like rules about how that is supposed to work. Like, if this one is A, then this thing is supposed to be filled in and that one isn't, and if it's B, then it goes the other way. Or there might be two fields that are either both populated or neither one of them are populated. And so these kind of data invariants, if you only have product types, if you only have things like records and objects, you can't encode them. But once you have some types, once you have the ability to say this or that or the other, you can have essentially the dependency between what data you have and what's the tag, right? Which, there's like a name for the different cases we call the tag, and that tag can determine what other data you have associated with it. And so that's a very common form of dependency, a very common kind of invariant that you otherwise have to make sure is true by hand and that you can enforce directly in the types. And those invariants, it seems like purely a thing about data, but can also capture properties of your program. You can say, when I'm in this state, I had better already have figured out the session identifier, right? So that kind of invariant is important, and you can sort of draw those invariants out of the data, the structure of the data. Another very common kind of invariant has to do with kind of simple type level tagging of information. So a common security problem that people have is like, what's his name? Little Bobby Tables. I don't know if anyone's seen the XKCD, where someone encodes some SQL injection attack by having what seems like an ordinary string, which gets sent to the SQL engine as if it's actual code, and someone names their name drop tables, and then like deletes your whole database because they put a funny name in. And what you really want to make sure is that when you get data from a user, you never feed it to the database without quoting it first. And this is a very simple invariant to encode in a type system. You just kind of have an abstract type that represents user data, and you have another type that represents quoted database strings. And you basically can check and make sure that the quoting, that you only allow something to become a quoted database string if somebody actually runs the function to do the quoting. And so in a dynamically typed language, you either have to just get that right by being really careful, which is hard, or you can do it in a kind of dynamic way where you have like some extra dynamic information which allows you to check at runtime. But doing it at the type level is both more efficient and kind of you can more efficiently like discover how that should flow through your code. Because type systems basically check invariants about how different parts of your programs hook together, and there's a kind of almost global flow analysis that the type checker does where it's like, I said in this one place that I needed to be quoted, and then it's going to kind of force me to like pass through the quoted strings until I get to the place where I decide to do the explicit conversion. And that's another very powerful kind of invariant and very common, useful one. Okay, so I guess that was the last question. So thank you very much.